my Orgo 2 lecture. I'm just messing around. It's a very difficult exam. I'm very
Oh.
afraid of it.
Okay. Sure, why not? Okay. No, that's true. Okay, the experiment we are doing today, nitration, and we are trying to do nitration of methyl benzoate, right? So you started with the toluene, you oxidize toluene to methyl benzoate for experiment 13, and now we're trying to nitrate methyl benzoate. This experiment, it covers reactions of aromatic ring. Basically, if you have a benzene ring that already has one substitution on it, that group that is already on the benzene ring is going to determine what would be the new product, or what would be the major product, what would be the minor product. So basically, the directing effect of the group that is already on the benzene ring is going to determine what should be the major product.
Actually, Professor, I do have one quick question.
Yes.
Since we can be relatively sure that we have a methyl benzoate solution, or product, I mean, from experiment 13, are we going to use that for 14 since these experiments are kind of like linked?
We can use it unless we have a pure sample out, so we can definitely use it. Can I ask one question? Is when you are asking question using your mic, does it show the video when we are doing experiment, or does it replace the video, or it doesn't? Because I'm not on the other side, I can't see. It replaces the video. If it does replace the video when we are just doing discussions, please use it's okay to use mic. And at the end of the lab, I always time for questions, and I want you to use your mic, use video for your questions, because then we have, at least we can see each other via computer screen. But when we are doing experiment, please try not to use the mic, because I'm trying to save these videos and I might use it later. I don't want, for your class it could be fine, but for the other classes it's better if it's not used. So if you could please just use the mic. You do not use the mic while we are doing the experiment. I appreciate it. So we can use the chemical from the last experiment. Definitely, I did do the IR, and I sent the IR spectrum for you. It did look pure, and since it was pure, then you would have to. Then you can use it definitely. So you please ask your question via chat. So the chat option is open. During the experiment, I always when I pause, that means that a question came up or a notification came up. I'm looking at the question just to make sure that if it's some, if it's a question related to the experiment, so I should stop and answer the question first. So please utilize the chat while when we start the experiment. Actually, okay. The theory for this experiment and the question for the experiment, or purpose for this experiment. What is the purpose for this experiment? So today we are studying with methyl benzoate, and we want to identify the product, and we want to make sure to identify the product as either ortho, meta, or para nitromethyl benzoate. Has aromatic compound they covered in your lecture already, so you know anything about ortho para isomers, or I need to explain that? Yes, perfect. So if we have ortho, which is the 1,2 position for the aromatic ring, para would be 1,3. Para would be 1,3, and I'm sorry, para would be 1,4, and methyl would be 1,3. And since it's new for some of the students, I'm going to put it on the board, and then we come back because I have to move the laptop battery and plug in. So it doesn't get me back. Okay, it's working. So if we have a benzene ring with methyl benzoate on it already, and we do nitration, the reagent for nitration, what's the reagent for nitration? Sulfuric acid mixed with nitric acid, that would be the reagent for the nitration experiment, which is going to generate or produce the nitronium ion with the NO2 plus, the nitronium ion. Nitronium ion is a very strong electrophile, and for those of you who have already been introduced to organic molecule to aromatic compounds, aromatic ring is very stable. For any type of reaction, we must have a strong an aggressive group to attack the aromatic ring, otherwise is not going to react with it. Like for simple bromination, is not going to react unless you add ferric chloride or ferric bromide as a catalyst to change the bromine to Br plus, and then Br plus as a very strong electrophile, then it can actually attack the benzene ring. In this case, is going to be NO2 plus. NO2 plus by nature is a very strong nucleophile, while a strong very strong electrophile, because this is electrophilic, very strong electrophile is looking for electrons. This is very unstable. Why is unstable? Because oxygen is highly electronegative, nitrogen is highly electronegative, and you cannot have positive charge, or they cannot handle the positive charge on the complex. So because it's very hard for it to handle the plus charge, this is going to classify it as very strong electrophile that can actually attack the benzene. How this one is created, the mechanism is explained in the lab manual, and I'm just going to explain it here one more time. So you have H2SO4 that is going to protonate NO2OH, or the nitric acid, HNO3. So you have your electrons, is going to remove one of these hydrogens, is going to be protonated. So you are going to get H2O plus NO2. Now, oxygen does not like the plus charge, and because oxygen doesn't like plus charge, and often you've seen in organic chemistry 1 also, that if you have a plus charge in the oxygen, you must remove H plus, so it ends up with OH, basically goes back. The other solution would be to make the H2O leave, and the plus charge would be moved. So the plus charge would stay with the parent compound. So in this case, the H2O is going to leave, and you end up with the NO2 plus. And this NO2 plus is going to act as your strong electrophile and is going to attack the benzene ring. For substitution reaction only, is not the addition reaction, is the substitution reaction. Now the question is, would the product be ortho, which is the ortho product? Is it going to be a meta product? or is it going to be para product? Is it going to be para product? Now, to answer that question, basically you are trying to decide which one is the major product, which one is the minor product. How would you decide for a compound or to be one of the products to be a major product or the minor product? What factors determine what's the major product in a chemical reaction that you have choice of more than one product? You have 2 or 3 products possible. What determines, what is the factor that is going to affect your major versus minor product? In a chemical reaction, in organic compound, the major product, it should always come from, or is always coming from, more stable intermediate. And that is going to reflect back to lower activation energy. So basically, in a chemical reaction, that is a 2-step reaction. And why do we know it's a 2-step reaction? Because intermediate forms. So if intermediate forms, this could not be that highly, exothermic. So you have the activation energy, you EA1, and then you have here EA2. The rate determining step is the slow step of the reaction. With the slow step of this reaction is going to be formation of the reactive intermediate. The reactive intermediate that is going to form here is a sigma complex. The sigma complex that is forming for organic aromatic compound is going to look like this. Let's say you have COOCH3 here. So when let's say if NO2 goes to meta position, NO2, because NO2 doesn't bring any electron, has a positive charge, is going to use the pair of electron from the ring to form the new bond. Since this carbon is losing a pi bond, this carbon is going to be unaffected, is not going to gain charge because this electron that is moving from here to this position still is shared for this carbon. So this carbon still has the 8 electrons, but the carbon adjacent is going to be plus charge. So you have still hydrogen here. So sigma complex for this reaction is when the electrophile comes in and before hydrogen leaves. So you have your sigma complex. This is going to form resonance. When it forms resonance, formation of resonance for the active intermediate is going to increase the stability of the intermediate compound that is, I should not say compound, the reactive intermediate that is forming. The more resonances you have, the more stable it is. So taking back, this is like a summary of something that you should know from lecture, and it's good to know for lecture. It is a stable intermediate is going to yield major product. Stable intermediate is coming from a path or the energy diagram that it requires less of the activation energy, or is going to require less of a delta H value. That means that intermediate is going to be more stable. If it's more stable, it's going to form faster. So more stable intermediate is going to form faster. More stable intermediate is going to yield to major product. So basically, if you want to find out which one is going to be major product, you have to draw resonances for all 3 intermediates and find out which one is going to be more stable intermediate. So when you compare, like, I'm just going to give one of the resonances for meta and para because I'm sure lecture is going to cover this and I don't want to take too much of your time teaching your lecture here, but you are in very good hands for your lecture. So I'm going to just compare this intermediate that is forming from meta with one of the resonances that is forming from ortho position. So if I bring the ortho here, hydrogen is there, OCH3. When this bond here is used for formation of the NO2, the carbon adjacent is going to take positive charge. So I call this one A, resonance, or I'm going to put ortho, resonance, and this is a meta. Resonance from meta intermediate, this is a resonance from ortho intermediate. Which one is more stable? Can you tell me O is more stable or M is more stable? Just looking at the two structure that I provide here, which one is more stable? M is more stable. Why O is not stable? What makes O unstable? Stability for the molecule is electron satisfaction, right? If the intermediate is satisfied with the electrons, is going to be with the octet, with the electronegativity, like desired, more tendency to accept. So you get negative charge on that part, so your Lewis structure more stable, or major resonance. So in this case, the resonance, you have to look at the arrangement of the electrons, a positive charge, where they are. What do you have here for the charge of the carbon? Is it positive or negative? You have a positive or partially positive charge for the carbon here. If you have an ortho attack, for the ortho attack, you would get a plus charge next to the carbon that is already positive. So you get two positive charge adjacent in neighboring carbons, and this is going to make the resonance not good. This is not a good resonance. And if it's not a good resonance, what does it mean? It's not stable. And wasn't this the intermediate for ortho? So my intermediate for ortho is not stable, and as a result, ortho is not going to be major product, because we learned that more stable intermediate is going to yield to major product. Between these two, this one is more stable compared to meta is more stable than the ortho, because the plus charge, it should never gets to this, even when you form the resonance. When you form the resonance, you're going to move the pi bond by one bond. Your kind of pi bond is moving, plus charge is jumping by two carbon, right? I'm not sure if that's how you are learning, but this is what I say. It's easier remembering for the students, like pi bond is going to move by one bond and plus charge is going to jump by two carbon. So basically the pi bond that is shared between these two carbon now is going to be shared between these two carbon, and this carbon feels electron deficient, is going to gain the plus charge. You see that the plus charge doesn't get a chance to reside here next to the carbon that is already positive. So it kind of bypasses that if you give ortho substitution. But if it's for meta substitution. If it's an ortho substitution, then plus charge is going to stay here, regardless of how you try not to get to that point. But one of the resonances is going to be like this. For para, is going to be just like ortho, and the plus charge is going to stay next to for the intermediate is going to stay here, and because this is positive, is not going to be stable. So that makes meta major. So we're going to have major product as the meta product. Well, you learn this in lecture. You don't have to come to the lab. You don't have to write a lab report to know this. But why we are doing this experiment in the lab? Because I want to make sure that you actually experience what you learn in lecture and know that if this is true, maybe other theories that you also learned, they are true. So we have to prove it in the lab that our product is meta product. So I talked to you slightly about the design of the experiment yesterday, and I said for any experiment, any design of any experiment, you should have a chemical reaction that you know what are your reactant, what's your product, which one is limiting reactant, which one is the excess compound. That's one thing. And then you have a procedure that you are going to follow to perform the experiment in order to get the product. Then you have to purify your product. Your product must be pure. And when your product is pure, if you are using recrystallization, distillation, extraction, any technique you are using to purify it, then you have to identify your compound and prove that your compound actually is meta and is not ortho or para in this case. Can you tell me what technique you are using today to defend your case that your product is going to be meta, not ortho or para? What is the identification? IR, unfortunately, IR is not going to work today because IR shows the IR shows the functional group. You're going to get a strong peak for CN single bond. You're going to get a peak for CO single bond. You would get a CO single bond. And those bonds or functional group are the same for all ortho, meta, or para substitutions or all three products. There is a way, like the position that is in the fingerprint area, and based on the fingerprint area, you should be able to determine you have an ortho or para using IR, but unfortunately, IR, it's not covered in depth that much in organic 2 in order to find out of ortho para or analyze to analyze the fingerprint area. You're just going for the other general functional groups. But if you had an NMR, it would make a huge difference. With NMR, if you have a meta, you would have a carbon that is between the two groups that is going to give you single singlet. And when we talk about chapter 17, I'm going to go back to these examples exactly. And if you remind me, I'm going to give you the structure of ortho, meta, and para again when we are talking about chapter 17 of the lab and show you how we can use NMR to determine the structure of the final product. It's very strong because if you have a meta position, then you have a single carbon between the nitrogen, the carbon-nitrogen bond and the carbon carboxylate bond for the ester functional group that is going to give you singlet. And you also have a doublet and you have a triplet. But if you have para, you would get only 2 signals and each one is going to be a doublet. So if you get 2 doublets, then you know that your substitutions or the product is a para. If you get 1 singlet, doublet, and triplet, then you have a meta. But if you have ortho, you're not going to get singlet. You only get a doublet and triplet, and based on that, then you can determine you have ortho, meta, or para. But I will draw the peaks for you when we are talking about NMR later. The technique, again, NMR. Yes, NMR. It would be, NMR can be used to determine the structure. But today, we are using melting point. Because the melting point for ortho product and para product is different from meta product, if the compound melts with the range that the compound with the meta substitutions is going to melt, then you can identify and map it back to product being meta, just like experiment 12, that you use the melting point in order to find out you have 2, 3, or 4 chlorobenzoic acid. So we learned about 2 experiments already. That the experiments, they were supposed to be under reflux because they required high heat. Today we are using cold system. We are keeping the reaction mixture cold. And can you tell me why the reaction mixture needs to stay cool, or the temperature should be low for today's experiments? prevent dinitration and trinitration. Yes, polynitration, it would be prevented. And how do we know we have dinitration or trinitration? The color for dinitration and the trinitro product is like a dark brown color. So if you get a dark brown color in the product while we are adding the nitronium ion, then that means that we have the impurities of dinitro and trinitro. If the color stays like a lighter yellow color or tan color, that means your compound is pure, and we can see that before even we do the melting point. Even the color is different. So how could you cause that dark color? If you don't put in ice, which is not good, that means you didn't follow the procedure at all. But if you put in the ice, both test tubes, and then you are adding 1 drop at the time, you wait between, is good. But if you don't wait and you add too much of the nitronium ion at the time, because the reaction is exothermic, is going to generate too much heat, and too much heat increase the temperature, regardless that you have the test tube in the ice. But the timing is not going to be enough to lower the temperature, and you will get byproduct. And because you're getting byproduct, if it turns like dark brown, you have to start all over again. But if it's a light yellow color, we can wash that with the recrystallization. It can go away, or we can continue. But if it's a dark brown color, to repeat it again, you have to start all over again. I'm going to start the experiment, and as we are performing the experiment, we will again continue talking about discussions. If you have any questions from the pre-lab, make sure you type it for me via chat, and I will answer your questions. The table, just one point before, there is a table for electron donor group and electron withdrawing group. If you have, in general, if you have electron withdrawing group, the other name for electron withdrawing group on the benzene ring is the meta director, like the carboxyl group that we have for ester, because carbon has a positive charge, is going to be electron withdrawing group, and it is a meta director. If you have an electron donor group, like for element that has pairs of unshared electron on the ring, is going to be for electron donor like a methoxy group or any alkoxy group like OCH3 or OCH2CH3. They are going to be activating, and when they activate, they only activate ortho and para position. They do not activate meta position, so they only activate ortho and para position. When they deactivate ortho and para position, so meta position is not deactivated, is much better than the ortho and para position. Okay, starting with the experiment, I have to first of all use gloves because these are like a strong acids. I'm going to use gloves and take the test tube with the sulfuric acid and the methyl benzoate. Okay, let me use my gloves and then I will continue. Take my gloves. My ice bath. I need the ice bath for the experiment. So I'm going to get the ice bath ready. Take 1 milliliter of the sulfuric acid, ice it, and then add 0.4 milliliter of methyl benzoate. I'm going to take the acid from Cupid and bring it here. I will be right back. I did not use graduate cylinder. I only used the dropper because 1 milliliter is about 20 drop. If I use the dropper, I get more accurate measurement than using 0.4 milliliters using a graduate cylinder. When the first milliliter is not graduated, and unless I have an automatic pipetter or a very accurate pipette placed here or set up for me, I prefer to use I count the drops. So I only counted like 8 drops for 0.4 milliliters, if you want to write that in your procedure. So for the next test tube, I need to get the acid, nitric acid, and sulfuric acid mixed, 0.5 milliliters of each. So that would be 10 drops of each. We place the nitronium ion in one test tube and the other one, the methyl benzoate with sulfuric acid in another test tube. Okay. Somehow the color for the acid mixture of methyl benzoate, it's not what I like. It wasn't supposed to be this dark of a yellow color. It should be like a tan. I'm gonna have to get maybe clean test tube and try again. Let me try the new test tube. So I'm not sure if something is contaminated or place an ice. The temperature is very important. It has to stay low for this reaction. And I didn't expect that yellow color. So it could be I didn't wait long enough when I had the sulfuric acid to add the methyl benzoate, or something is wrong with the chemical. I hope nothing is wrong with the chemical, because that's the last thing I wish for. Then I won't get the product. We look at your questions. 0.4 milliliters for methyl benzoate. So that means like every 2 drops would be 0.1 drops. That's why I use. Okay. It's giving me same problem. Maybe I can continue and hope for the best results. Okay, this other new methyl benzoate has a lighter color, so I'm going to use this one. And I'm not using what I had earlier. Wait for the temperature to drop. Okay. The color is not clear, but it was a lighter yellow color than the other one that I had. So it's like a less colorful than the other one. Yes. Going to wait for the 5 degrees Celsius temperature for the test tube before I add the nitronium ion. Have any questions while we're waiting? We are in step 3. Slowly, yes. Yes. Do your gloves change this color? It's time to change gloves. Yellow color and these gloves. Meaning that I touched acid already. Why is the pipette in the ice? That pipette, I'm not using it. I just left it in the test tube. I am using a new pipette for the mixture. So this is basically a discard. I don't need it. Okay. Going to add the nitronium ion. 1 drop at the time to the methyl benzoate mixture. I'm going to mix it and wait one thing is not working. One of the chemicals is contaminated this study. You know what I'm going to do? I'm going to use the nitric acid that you made, not the nitric acid, methyl benzoate that we prepared last class. In case if the methyl benzoate is a problem, then we should get better color. It would be actually nice to see that. If it works better, it would be nice. Let's count my drops. 1, okay. Screenshots. We get to the screenshots soon. You can take the screenshot. Can you see from here, or can take a screenshot of the setup at this point? Yes, you take a screenshot. I'm going to use this just to stir it. one of the chemical is contaminated. I cannot figure out which one. I hope we could still get the product. And maybe with some byproducts. But the color is not even color of dinitro product. It's a new color. Yes, it is. Yes. It could be that would be the. I had experience in the past that when the nitric acid was contaminated, one time actually I had to go from North Campus to South Campus to get a new bottle of nitric acid in order to perform my experiment. So I'm not surprised if the same thing has happened. But to follow the procedure, you have to leave this to go to room temperature. We wait for 15 minutes, and then we are going to see if actually it's working or not. Going to continue also with the methyl benzoate from last lab. Even though it looks very similar, but still I have two sets of experiments. I'm just doing two experiments at the same time, parallel, because we have time. We are waiting for 15 minutes for the other reaction mixtures to get ready. So while we are waiting for that, I'm also trying with the methyl benzoate, which we prepared last class. It's better to have two samples in case one works better than the other. We are still step 3. We are still step 3. For one of the reaction, I have it step 4, one set. The other set is step 3. Just adding one drop at the time. So if the color doesn't stay like light yellow, has nothing to do with the heat that is being generated. it could be the contamination of the nitric acid. Because I'm carefully just one drop at a time. It's not just the sulfuric acid. I'm dropping one drop at a time of the nitronium ion. Nitronium ion is mixture of sulfuric and nitric acid. Is the solutions that you prepare in step 2. Yes. Very good. Thank you for responding. Okay. So I have 2 separate trials. Has it been 15 minutes for the first test tube or not yet?
Sorry, I never set a timer.
Okay. Going to keep 10 more minutes to make sure that it is long enough. Okay, while we are waiting, I can answer your questions. I also need to prepare the ice, which I think is too early. It could melt. For the first compound. More. Two. Okay, I can go back to the chat record. I can tell you what is timeline for that. Okay. 2 more minutes. Couple more minutes. So far is 1, yes. Just waiting for the finish, for the reaction to complete, and I still hope that we get the product, we get precipitate. And if we don't get precipitate, I'm not sure how we can prove this. We have to have new bottle of nitric acid. Okay, what time do we have? 35? Pre-lab 12 only, not 13. I have to grade pre-lab 13. Okay, I'm going to try the first, first test tube or the first reaction mixture using ice in a 50 ml beaker up to the mark of 10. So I fill up the beaker up to mark ice, and I'm going to get this water out. Now I pour the sample over the ice.
The audio and video is crashing.
You can take a screenshot of this actually precipitated formula, which is a good thing. You can take a screenshot and go back. So the video done. Sometimes the poor student and the video automatically stops. So we actually got the good thing. See, it's cloudy. It's precipitate. I have white precipitate.
Professor, unfortunately, your video is not training anymore. It's possible for you to log in and then log back.
When the connection is weak, video. Okay, good. And I, your, the concern again on the chat. Using the chat, I try to keep up with it. That's a good thing, actually. The contamination, whatever it was, it didn't prevent the formation of the crystals. Okay, while I'm waiting for these crystals to complete, I'm going to just place in ice for extra. And prepare the vacuum filtration. You remember the vacuum filtration setup? I have to use the vacuum pump and a vacuum flask. Okay, just leaving in the ice. Why is the connection so low? I have no idea. So weak. Okay. Repeat the screenshot? Sure. You can take a screenshot of this product after putting it over the ice. Okay. What are the next steps? Filtration, vacuum filtration, and after vacuum filtration, what's the next step? To wash it. So what's the purpose of washing with water? Washing with water would remove, what is going to remove? What will be removed when you are washing with water?
Any impurities that are water soluble?
To remove contamination that they are water soluble. Okay. Take a screenshot of the mass of filter paper. Does it show the number? Yes. Okay. 0.181. Mass of the filter paper. Turn on the vacuum first. And pour the mixture carefully over the, maybe I should wait until it's over the filter paper. We don't have a lot of product, and that's understood because this is basically a micro scale experiment. We only start with 0.4 gram of the, or 0.4 milliliter of methyl benzoate. So I don't expect to get a lot of product. Considering with the 0.4 milliliter, we have enough product for the reaction. Can you find the theoretical value for methyl, nitro, methyl benzoate if you don't have it already? Please.
Sir, can you please repeat that? The audio cut out.
The product. Melting point for the product. Can you find the melting point for your product? Not the theoretical value, literature value. Theoretical value represents the mass. So we are looking for literature value. Going to wash the sample with sodium bicarbonate. Next step, washing the sample with sodium bicarbonate. Continue by washing with cold water. And your next step, what's the next step? Recrystallization with methanol, right? Recrystallization of your sample with methanol. Going to transfer the crude product the product before recrystallization. I have the crude product. Transfer that into a container, a flask. I'm going to do beaker today. I'm replacing. It's going to be the same. Not going to make a difference what container I'm using, but I'm using beaker because it's easier for me to transfer back. What is the suggested volume for methanol? No suggested volume, just the minimum amount. As much as it would help to dissolve the sample. Okay, transferred completely. I am using some methanol to wash the product from filter paper. To make sure everything is transferred. And start heating the sample to dissolve at high temperature. Then cool it down to room temperature, then place in ice. That's the recrystallization. We heat the solid sample with minimum amount of the solvent, recrystallization solvent, dissolve it at high temperature, cool it down to room temperature, then place in ice bath for complete recrystallization. to recover the crystal back at lower temperature. Describe the recrystallization process. Recrystallization, you are going to dissolve your sample in proper recrystallization solvent at high temperature. Then we are going to leave it on the side to reach the room temperature, basically cooling slowly. You cannot do sudden cooling for recrystallization, because if you do sudden cooling, it would trap the impurities and it could trap the solvent. If it traps impurities, you would get impure product. If the compound traps the sample traps the solvent, you would get oily product. So it would oil out instead of you get solid compound. So when the sample in the mixture reaches room temperature, or basically when you see some crystals forming, then you can place it in ice bath for complete recrystallization. Why ice bath? Because the lower the temperature, the lower the solubility. So basically when you place in ice, you lower the solubility for maximum recovery of your crystals. And when you have your crystals, you continue with the vacuum filtration. After 5 minutes in the ice, you would place in the vacuum filtration 5 minutes to run the extra 5 minutes to get most of the moisture away. Then you would place in the oven to dry. Did you find the melting point? Because I'm trying to set the temperature for oven. That's why I asked you to find the temperature. Melting point.
78 degrees.
Okay. Boiling point for methanol is 65, and that is 78. So I'm going to place the setting at 70 degrees for the oven, and I'll be right back. It's getting cloudy, which hopefully they are getting crystals. I put in the ice. Okay. I'm going to place in ice. If I don't get any precipitate, that means I have used more than enough solvent, which makes me put it back on the hot plate, reduce the solvent. I will try it first. If I don't get any precipitate, I will place it in on a hot plate to lower the volume for the solvent, because your solution must be saturated and it should be cold temperature, low temperature, in order to get the maximum crystals back. You recover most of the crystals. Okay, perfect. Let me check mass for another filter paper. If it's the same, you have it already. If not, I'll let you know what is the mass. Okay, this is the same one as you had before, so we're going to use that same mass. Okay, perfect. Crystals are forming. I'm using methanol to wet the filter paper, because if I use water, then 70 degree of the oven is not going to be high temperature enough to evaporate the water. So I try to avoid any water. And I'm leaving the methanol in ice bath to cool off. So when I'm trying to wash the precipitate, I wash it with cold methanol rather than room temperature methanol. Oh, cold methanol. You remember when I put in the sample on a hot plate in hot methanol, it dissolved? If I use room temperature, it can dissolve some of the or the crystals. So I'm trying to avoid dissolving any crystal while I'm doing filtration. So for washing purpose, last step, I should use cold methanol or cold solvent in general instead of the room temperature or hot. Okay, turning on the vacuum. I guess it needs to be connected. You can take one more screenshot from the vacuum filtration of the final product. So in case if you miss one or two of the previous screenshots, you could replace these. Everything is transferred. And I'm going to wash it with cold methanol. Run vacuum for 5 minutes. Okay. Since our first setup, first test tube, we got proper product. I'm not using the second setup. You see this white crystals up there? There's no yellow or brown crystals. So our product looks fine. I don't have to continue with the second set that I left it on the inside the test tube earlier. Whenever you think it's 5 minutes, you let me know. You lost me again? Even the mic is not working? Mic is not working or no? It's working. It looks like it's working now, so I'm sorry. I hope that the video doesn't get too sloppy. Oh gosh. Has it been 5 minutes? No? Okay. Since 5 minutes since I start the vacuum. Because we continue the vacuum for 5 minutes. 3. Okay, wait for 2 more minutes. Then we place it up. You don't have to leave the session to come back for the mic to work. I think if you just, for me, if I stop the mic or disconnect the mic and I go back to it, it works better. Okay, it's the weather then. Okay. Okay. Going to turn off the vacuum and try to get the sample, place it in a watch glass. The sample, the crystals look all right.
Have we weighed the watch glass?
No, I'm not going to weigh it later because I have the mass of the filter paper. I'm using the mass of the filter paper only. As long as you stay consistent, if you stay consistent with what you with what you started with. Let's say if you have the mass of the filter paper only, you have the mass of filter paper and the product, you can get the mass of product. But if it's the watch glass, you have to have mass of watch glass filter paper to begin with empty, then watch glass filter paper and the product at the end of the reaction. So if you stay consistent, you can get the mass of the product without the watch glass. So I'm waiting for like 5 minutes. I have to be careful with this oven. I don't want to get the sample melting in the oven because the solvent is methanol. It evaporates much faster than water. So like in 2 minutes, I'm going to try and then continue to get some. Okay, is there any questions? Tomorrow's lab we meet at 12:30. Yes. We do have lab tomorrow. Yes, the only problem is I don't have a correct answer posted there. What I have instead is it's just a grade. So if you didn't get a complete grade, I hope that at this point you already know the answer because during the pre-lab discussions we talked about the answers for every question, especially for the 12, and you can see the answers that you add. Yes, you can see your answers definitely, and you could see the grade. And if there is something wrong with the answer, you have lower grade. Not yet. After I grade it, then you can see your answers. After I grade, then I will set up for you to see your answer and your grade at the same time. I have not set up the experiment 12 for you to see the answers, but I will. You get the sample from here, so it doesn't. Okay. 5 minutes. Gonna get the mass for the product. Okay. Go ahead and record take a screenshot to record the mass for product. You got it? 0.479, that was the number. 75, okay. This is with the filter paper, exactly. Yes, with the filter paper. What's next step? Next step, to find the melting range. And if it does melt, this close to the melting point for metal, it's proven that the product is metal. Okay, going to prepare the sample. Use a capillary tube. Capillary tube, pass it through the hollow glass tube. Placing the sample. And monitor. I'm not sure if I bring the laptop close to the eyepiece, you can see the melting. Can you see the melting, or is blurry? It's blurry. Okay. I was trying to see. You see the time of the melting, so we could record the temperature based on what your observation. But if it's blurry, then you have to just trust me. If it's hard to see, then I'm going to monitor and let you know as soon as is melted. And while we are waiting for this, I am going to open the quizzes for, not the quiz, show the answers for pre-lab 12. The brown precipitate that you had on the filter paper, it was not permanganate. Permanganate is a purple color. With the user's answers, so it should give you the questions with your answers for later. Still is 50 degrees, the sample has not melted, which is a good news. It doesn't look like that is contaminated. It looks like it's pure. Because we don't want it to melt before 65. Because if it does melt before 65, the sample is not dry. If it melts before the boiling point of the solvent, okay, perfect. It's good to be sure of what is needed. But for the mass, as I said, you have to have the mass of the product. That's your concern. So if you have the watch glass to begin with, you would measure the mass of watch glass later. But if you don't have the mass of the watch glass to begin with, there is no reason for you to measure the mass of watch glass later. Okay, it's 66 and is not melted yet, which is a good thing. Not longer to melt, not, but if it melts below the melting point, I'm sorry, if it melts below the boiling point of your solvent, that means your compound is not dry. And instead of melting, it's just being dissolved in that solvent. Our solvent, in this case, was methanol with the boiling point of 65. So we don't want the sample to melt below 65, because if it melts below 65, that means it's actually dissolving in methanol. So if you have your sample, you add a drop of methanol, you heat up to 65, it will dissolve. So you don't want that to happen. So it should not melt below boiling point for your solvent. Okay. Melted at 76. 76. Yes. Then I stopped it at 78. The range is 76 to 78. Yes, final 78. Okay. IR machine is here. It runs by a program. I already have the sample, the IR of your sample, which I performed the experiment the other day for the methyl benzoate, and I sent you via email or announcement, one or the other. So did you get the IR spectrum for your experiment? You all have the IR spectrum. Perfect. Yeah. Do you have any questions? Any questions?
Yes, Professor.
Yes.
When I uploaded the IR into the lab for experiment 13, like the procedure said for us to do, I included the explanation there that I would have put in my lab report. Is that okay?
Your discussion, your conclusion should have the data from the IR spectrum, because the IR spectrum is basically showing the showing the location of the peak for CO double bond, which is for conjugated ester, is at 1718. For conjugated ester, that's the perfect number, and it proves that yes, you do have ester for the product. So it would be better to include in the conclusion as well.
Understood. I will do my lab report. Thank you.
And you can re-upload before it's due as many times as you want, because I grade the last submission. Because when we perform the experiment, I don't know, it turned dark, so maybe just light sensitive, motion sensitive. So when we defend our case that yes, this is the product that ester has formed, we have to base our defense based on the numbers and the information that we get the data. So that's why it should go into the conclusion and abstract. Those numbers it should show there as values or measured values, data value. Okay, do you have any questions for me? If you have a question about the experiment, I'm going to keep the recording, but it is not a question for, you could still use the chat, please, for questions about the experiment. And if you don't have question about the experiment, it's just other concerns, then I can stop the recording because I want to take attendance. Then you could ask your questions. Do you have any question about today's experiment? No? Okay. Let me stop the recording. It's not end of the class yet. We have other discussions. I'm just going to stop the recording so we could continue discussions and taking attendance.